Gluconeogenesis. So what does gluconeogenesis mean? Yeah, creating some new glucose, right? So, and that's what we're doing. So gluconeogenesis really looks remarkably, with a couple exceptions, but remarkably like the reverse of glycolysis. We're going to take our pyruvate and we're going to turn that back into glucose. Now you take in glucose from your diet and then it's transferred off to your cells. So why might your cells ever need to make glucose? So you can't constantly intake glucose. So especially if, your plane crashes in the middle of nowhere and you starve for several days. So this is when this becomes super important. So it's important in other cases, but that's when it's really important. So because there are certain parts of your body that really strongly prefer glucose as their substrate, like your brain and your red blood cells. Turns out your brain can actually start using other stuff called ketone bodies somewhere down the road, but you got to be starving for 7 or 8 days before that ever happens. So during those first 7 or 8 days of starvation, your brain is not thinking so well. So here you've crashed in the middle of nowhere, and you need your wits about you to get out alive, and unfortunately your brain's not functioning properly because you don't have enough glucose. So, or at least, hopefully this is doing its job to get you some glucose. Your liver can create some glucose, release it into the bloodstream, and hopefully, at least for a time, keep your brain functioning properly, even during starvation. So, but gluconeogenesis, the purpose is to turn pyruvate into glucose. So, and this pyruvate might not necessarily have come from pyruvate. So per se, we can turn amino acids, certain amino acids of pyruvate. We can turn lactate, which was the end product of glycolysis. We can turn it back into pyruvate. We can also turn some other amino acids into oxaloacetate, which is part of this reverse process. It's one of the major differences here right at the end. Cool. So unfortunately, the handout you guys have is black and white. I'm actually, for the first time ever, going to try and post this with the video. So if you want it in color, you can get it. So, because highlighted in red down here and in red up towards the top, so are a couple of the key differences between gluconeogenesis and glycolysis. So for all the reversible steps that we talked about in glycolysis, they just use the same enzyme, just go in the other direction. So they're reversible. Their delta Gs are close to 0. They can shift the equilibrium one way or the other, depending on which way we want to go. But the irreversible steps, which were often the major regulatory steps, there we got some issues. Cool. What was it that turned phosphoenol pyruvate into pyruvate? Pyruvate kinase. Pyruvate kinase ain't going to get you back. So we're going to have to take a different pathway then. And this is the big major difference. We'll see one other up top, but this is the big major difference we're going to see here. And so we can't just turn pyruvate back into phosphoenol pyruvate. Turns out we got to go through an intermediate oxaloacetate, which we'll see again in the citric acid cycle. So pyruvate carboxylase turns pyruvate into oxaloacetate. How many carbons does pyruvate have? Got 3. How many carbons does oxaloacetate have? We haven't talked about it yet, but it is in the CAC. It's got 4. So if I'm going to turn a 3-carbon substrate into a 4-carbon product, what needs to happen? I need to add a carbon, and usually we'll see that we add or lose carbons in the form of CO2. So, and it gets added as a carboxyl group, hence the name pyruvate carboxylase. It's carboxylating pyruvate. So it makes sense. We added a carbon, in this case in the form of a carboxyl group. So we have a problem though. So in this case, so our pyruvate, which maybe came from lactate, let's say, or something like that. So, and where did the lactate probably come from? End result maybe of glycolysis. And where does that happen? In the cytosol. Here's our first problem. Pyruvate carboxylase ain't in the cytosol. It's in the mitochondria. So there's our first issue. We want this to happen, but it can't if it's in the cytosol. So what do we need to do with this pyruvate? we need to shuttle it off to the mitochondria. And then in the mitochondria, we can convert it to oxaloacetate. Cool, because in a minute, we're going to turn this oxaloacetate back into phosphoenol pyruvate. And the rest of this takes place back in the cytosol again, which means now what do I need to do with oxaloacetate? Yeah, I want to transfer it back out of the mitochondria, but we have a problem. He can't get out of the mitochondria. So there's no transporter for that. Can't do it. He won't leave the mitochondria. Well, that sucks. So we found him. We need to make him. He's the next step in the pathway for gluconeogenesis, but he's in the mitochondria and he can't get out. So we turn him into malate. Cool. And what's great is malate can get out of the mitochondria. So we ship this malate off to the cytosol, and guess what we do with it? We turn it back into oxaloacetate. So I like to think of this as the cell being a little bit crafty in the engineering here. So we need to turn pyruvate into oxaloacetate. Unfortunately, that can only happen in the mitochondria. That's the only place pyruvate carboxylase exists. So we got to ship it to the mitochondria. Once it's oxaloacetate, though, it's stuck. It can't get back out of the mitochondria as oxaloacetate. There's no transport for that. So we turn it into malate, for which there is a transport, and you can transport that back out into the cytosol. Now that it's in the cytosol, then I turn it back into oxaloacetate, the reverse of the step we just did. And now that it's oxaloacetate, now I can make my way up to the next step. And with PEP, phosphoenol pyruvate carboxykinase, now I can turn it into phosphoenol pyruvate. Cool. Lots of work to accomplish this. And a couple things we need to look at. So here, PEP carboxy what? Kinase. What's really commonly, do we associate with kinases? So phosphorylation. In this case, what's involved? Ooh, it's not ATP in this case. It's actually GTP hydrolysis. That's kind of funky. This happens on occasion, where instead of GTP-GDP interconversions, or I'm sorry, ATP-ADP, we do GTP-GDP. So, but essentially this is functionally equivalent to ATP and ADP. Cool, so instead of ATP hydrolysis, this kinase is GTP hydrolysis. So, but it did involve phosphorylation with hydrolysis of something analogous to ATP. So, and then back over here, so with our pyruvate carboxylase, if you recall, in going from phosphoenol pyruvate to pyruvate, so it was a big downhill reaction, right? So we're going uphill. Costs energy to go uphill for this step, but it also costs energy back here as well. So making glucose ain't cheap. We get 2 ATP net production, right, in glycolysis. It costs a lot more ATP to go back. Cool. This is the biggest difference, so between glycolysis and gluconeogenesis. So, because notice now that we're phosphoenol pyruvate, so we'll go to 2-phosphoglycerate, 3-phosphoglycerate, to 1,3-bisphosphoglycerate with all the same enzymes all the way back till we get to fructose 1,6-bisphosphate. All the same enzymes all the way back. So, but then we have one other enzyme there as well that we didn't use in glycolysis. And again, it's the big downhill steps in glycolysis that were irreversible that we're going to have to find a different pathway back. And those are the ones that need a different enzyme. So in going from fructose 6-phosphate to fructose 1,6-bisphosphate, what was our big enzyme that did that? That was a big major regulatory step? PFK1. Going the other direction, we're not using PFK1 this time. Cool. New class of enzyme. Phosphatases. Phosphatases. So kinases, we usually associate those, again, one with hydrolysis of ATP or maybe GTP, as we just saw, but usually ATP, and also something getting phosphorylated. But a phosphatase usually results in the exact opposite. Instead of something getting phosphorylated, something's usually getting dephosphorylated, we say. And notice here, fructose 1,6-bisphosphate, one of those phosphates is getting hydrolyzed off, dephosphorylated, the one that was at carbon number 1. And we just ended with fructose 6-phosphate. We'll see this pattern as well. So again, phosphatases usually remove a phosphate, hydrolyze a phosphate off of the substrate. So it leaves the inorganic phosphate in this case. So if you notice, there's quite a few times, like when I say that ATP goes to ADP, I never drew in the inorganic phosphate there either. I have a lot, and actually I didn't even show the waters. I have a lot of unbalanced reactions like that. Same thing with the NADs and NADHs. I didn't balance them out. I wanted to keep it as simple as possible because we can fill up this diagram with a lot of other stuff quick and make it really confusing.
So we're worrying about like magnesium and potassium and all those little cofactors. You don't think that's something to worry about knowing?
Ooh, as far as if magnesium is involved in stuff like that, or a couple places where, say, like thiamine pyrophosphate might be involved, those cofactors, they're all actually really important.
Okay, so know all.
Yeah, know all those lovely little cofactors, and especially knowing magnesium is involved too.
Right, which is it's almost in everything, right? So it's not.
Almost. Cool. So once we got our fructose 6-phosphate, where are we headed after that? Glucose 6-phosphate. And there's nothing new about that, but where are we headed after that? We're headed back to glucose. Who turned glucose into glucose 6-phosphate? Hexokinase. What was the delta G for that step, if you look back on your sheet? Not the delta G not prime, but just the regular delta G. So negative 34. Okay. What does that mean? So very, probably irreversible. Very spontaneous, very irreversible. And again, it's the irreversible steps where we probably need a new enzyme. So enzymes are great for reversible reactions that go in both directions, but for the irreversible ones, they usually go one way only. So in this case, hexokinase is not going to cut the mustard. Who are we using instead? And here's our second example of phosphatase. It just hydrolyzes off a phosphate. Sweet. And then this glucose now can get released from the cell back into the bloodstream, maybe, yada, 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 yada. Cool. Note one other entry point on here was glycerol. Glycerol is a 3-carbon alcohol, or actually really a triol. So, and glycerol can come from fatty acids metabolism, and so that's another shuttle into gluconeogenesis. So notice one thing to keep track of on gluconeogenesis, your sources for getting into the chain here. Lactate, the big one, where we're kind of assuming we started, but also there are various amino acids that can enter into a couple of different entry points, as well as glycerol.
We don't have to know each amino acid, just know that it's some.
I don't know that you got to know each amino acid. I would look at how much detail he gave in the slide. He actually showed which ones, but that's a lot. So I would make it one of the last things I memorized if I, had all the brain capacity in the world and all the time before Monday night. Maybe I would, but that would probably be one of the last things I memorized. So, but definitely know that there you got, some different entry points into this. Cool.
This is all happening in the cytosol as well.
So this is all happening in the cytosol as well, except for those little part that was happening in the mitochondria. Sweet. Cool, couple of things. Before we actually focus on the enzymes, if you look at the little table. So if you look at gluconeogenesis control, under activation, So here's some really general things. What kind of things activate gluconeogenesis? Lactate's the first one. Does that make sense? So why would it make sense for lactate to kind of turn this on? Well, because it's kind of what could start this off. You got lots of lactate, might be good to go this way. Okay. So glycerol can also turn it on. That's another entry point, so that kind of makes sense. Certain amino acids, if you got a buildup of them, then hey, let's use them to make some glucose maybe. So buildup of any entry point into the cycle can turn this on. Okay, what else can turn this on? High-fat diet or prolonged fasting. It's not there. So high-fat diets and prolonged fasting. So either eat lots of fat or don't eat anything at all, and you can get this going. So why would a high-fat diet? So could be the glycerol, but maybe better reading. If you got a high-fat diet, what is it probably low in? Carbohydrates. And if it's low in carbohydrates, then maybe there's not enough glucose in your bloodstream for your brain and your red blood cells and all that stuff. So maybe it'd be a good idea if we made some. Prolonged fasting was kind of the one we already addressed with being shipwrecked or crashing a plane or whatever. So if you just don't have any food, you might need some glucose in your bloodstream for your brain and your red blood cells. What inhibits gluconeogenesis? High carb diet. Why would a high carb diet inhibit this? You already got plenty of glucose. Let's not waste any energy making more because it's pretty expensive to make it, right? So, and then last but not least, insulin. So what is insulin? When does your body release that? When does your pancreas really release it? When you got lots of glucose in your blood. So if you've already got lots of glucose in your blood, there you go. Glucose in your blood, then you don't need to do this. Sweet, well, let's focus on those enzymes. So one thing to note, if you guys haven't figured out, so both Dr. Leffler and Dr. Hendrickson are huge, huge, huge health buffs. So if you haven't figured that out, huge health buffs. And so when they start talking about things and talking about it with association to disease, so pay attention. Keep those things in mind, especially if they feel the need to make a slide about a certain disease. You need to know about that. So I'm not going to talk about it tonight, but those are things you need to know. Again, you're going to want to go back through every single slide before Monday. A lot of them probably 2 or 3 times. So pyruvate carboxylase. What does he do again? So it turns pyruvate into oxaloacetate, starting our way back up the chain. So he's activated by acetyl-CoA. Activated by acetyl-CoA. Does that make sense? So here's where you're like, well, if I had a buildup of acetyl-CoA, I could think of maybe turning on the CAC cycle too or something like that. So could go either way. Acetyl-CoA can feed into the CAC cycle or into gluconeogenesis. It can kind of go potentially one direction or the other. And so it can kind of make sense and it can kind of not make sense at the same time. So what do you need to just do? Memorize it. Sweet. So PEP carboxykinase. So again, your PEP carboxykinase is what turns the oxaloacetate into phosphoenol pyruvate. So keep that in mind. So hormonal synthesis, that's it. You don't really got to get any more specific than that. That's another just memorize it. So fructose 1,6-bisphosphatase, turning fructose 1,6-bisphosphate into fructose 6-phosphate. ATP turns it on. Does this make sense? Well, notice we talked about glycolysis. What would ATP, if it affected an enzyme, how would ATP affect that enzyme in all likelihood for glycolysis? It inhibited it. Sweet. Notice glycolysis is working on metabolizing glucose to pyruvate, and then on, and so this is going the opposite direction. What often activates glycolysis inhibits gluconeogenesis and vice versa. Notice what would happen if glycolysis and gluconeogenesis were running full tilt at the same time. You'd be going in a giant circle. And the problem is that glycolysis doesn't produce as much energy as gluconeogenesis uses up. And you just use up all the cell's ATP. It'd be a waste, a complete and utter waste. So in this case, substrate cycling, because things can often go one direction or the other, we talk about substrate cycling. It makes sense that if you turn on one pathway, you better turn the other one off at the same time. So if it makes sense that ATP turns off glycolysis, then it should also make sense that it turns on gluconeogenesis. So, cool. If we got plenty of energy, then maybe we find a way to store some of it long term. So, AMP, does this make sense? Yeah, AMP often shuts down enzymes in glycolysis. Often activates enzyme in glycolysis, and so it makes sense that it's going to inhibit the ones for gluconeogenesis. We don't want both cycles going on at the same time. So, and finally, another one here to memorize, fructose 2,6-bisphosphate. Cool, glucose 6-phosphatase. Top of the chain there, glucose 6-phosphatase was turning glucose 6-phosphate into glucose. Does it make sense that glucose 6-phosphate would turn it on? Yeah, that's the reactant for that step turning it on. Would it make sense that glucose turns it off? Yeah, notice this is the one out of everything on here, this is the one that you can make the most sense of. The reactant turns it on, the product turns it off. Sweet.